Hello wonderful person, this is Anton, and in this video we're going to be discussing an intriguing new paper that tries to tackle the mystery of dark matter. But it does so in a very unique way. It actually compares the idea of dark matter to a very peculiar state of matter that we know exists here on Earth and we can actually produce in a typical lab environment. This right here is known as BAC, Bose-Einstein condensate, sometimes also referred to as the fifth state of matter, because unlike solids, liquids, gas, or plasma, BACs can also exist for a very long time in certain conditions. Pretty much any matter can become this, but it also contains a lot of properties that other states of matter do not possess. And so in this video I wanted to explore this idea a little bit more, because what the scientists have recently identified by using simulations and relatively complex math analysis potentially provides a very interesting explanation to the mystery of what exactly is dark matter. The mystery of expecting to see a lot of invisible matter out there based on various effects and based on a lot of gravitational lensing from various distant galactic clusters, as well as effects from various galaxies where the stars are moving way faster than they should be moving based on all of the observable matter and all of the gas. And so, as you might have seen from previous videos, which by the way should be in the description, in the past there have been quite a lot of different explanations for what exactly is dark matter. And not so long ago, one of the recent papers was able to sort of definitively show that dark matter is unlikely to be some kind of a very large, very massive particle. The concept scientists refer to as WIMPs, weak interacting massive particles. And the recent studies suggest that it's unlikely to be that, but it can still be at least two other things. An intriguing other particle known as axion that is actually meant to explain something entirely different in physics, with the explanations about this somewhere in the description, or potentially a bunch of particles that are just extremely low in mass, or low in energy, and are thus just extremely difficult to detect. And it's that last explanation of these very small, very low in mass particles that the scientists wanted to focus on. Specifically, they actually wanted to simulate what would happen if you had very low in energy particles, more or less interacting across large volumes of space. And so by using relatively complex simulations, they were able to create something that's thousands of light years in length, to some extent representing a center of a typical galaxy. But intriguingly, what they discovered is that these particles will actually start exhibiting quite a lot of effects similar to a typical quantum system. In other words, because of their low mass, they start having what's known as wave interference, which start producing a lot of turbulent effects, including various vortices, and a lot of fluctuations that are a little bit different from what we expect from a typical gravitational system. But more importantly, it reminded the scientists of something that we actually can make right here in a typical lab on Earth, and something that's entirely quantum in nature. And so here I wanted to briefly explain what exactly a BAC is. Originally described and predicted by Einstein and an Indian physicist, Satyendra Bose. And in a nutshell, it explains how certain particles, which we usually refer to as bosons, in certain extremely cold conditions and also in relatively low densities, will start increasing their interference waves until those waves start interacting so much that they actually turn into one massive wave that starts to acquire not microscopic but macroscopic properties. It basically becomes a single collective quantum wave. And it's this unusual quantum wave that can easily contain hundreds, thousands, or even millions of different particles that then starts to exhibit these quantum effects that become visible on a much larger scale. In other words, the actual particles disappear and they become basically a large massive wave. Okay, honestly, it's kind of difficult to imagine exactly what this becomes, but here's how it's visualized by NASA. And here's how it's visualized by the National Institute of Standards and Technology. And a lot of modern studies in quantum physics usually rely on Bose-Einstein condensates to try to figure out exactly how quantum effects work and what happens in certain conditions. More intriguingly, in one of the recent studies, and I think this was like a study from a couple of days ago, the scientists were definitively able to show that the famous EPR experiment that basically proved the non-locality of the universe definitely seems to work for BACs as well. Or in other words, you can actually affect one BAC, quantum entangled to another BAC, and both of them will have entanglement effects no matter how far away they are, even if you place one of them hundreds of light years away from planet Earth. Now we're actually going to be exploring this idea a little bit more in one of the future videos, so do subscribe if you want to learn more. But in a nutshell, this is a proof that even really large objects, containing hundreds, thousands, and millions of atoms, once entangled and once they achieve a quantum state, will actually possess all of the quantum properties we expect. But we'll talk more about this in some of the future videos. For now, let's focus on BACs and how it connects to dark matter. So basically Bags are a state of matter that's assumed when a bunch of particles, in this case bosons, sort of connect their interference wave, basically combine into one large massive particle, or technically a large massive wave. That of course relates to the idea of particle-wave duality. And so when the scientists were conducting these experiments with hypothetical dark matter of extremely low mass and low energy, they actually realized that it seems to possess extremely similar properties to a typical Bag. And so even though we generally associate dark matter with something related to gravity, which basically forms the cornerstone of entire cosmology, this particular simulation and this experiment sort of directly connected this to ultra-cold atomic physics, describing behavior of cloud of atoms, specifically atoms like rubidium and potassium, as an unusually similar model to what we might observe with hypothetical dark matter particles, and more importantly connecting this to an idea that already exists. An idea in cosmology known as fuzzy cold dark matter, or the idea that involves these extremely low in mass particles potentially being responsible for all of the dark matter effects that we're observing from around the universe. And particles whose wavelengths would have to be extremely long, possibly a few light years in length, making them practically undetectable by modern techniques. But because they're present in very cold conditions and because their wavelengths are already so long, at some point they would start interacting with one another and eventually form some kind of a very large collective, entirely quantum in nature, but also possessing a lot of effects that we still do not understand very well. And so basically by bringing two disciplines into this, the discipline of cosmology and ultra-cold atomic physics, the scientists actually found a really intriguing way to potentially solve this mystery. But I guess more importantly, presenting us with an opportunity to study this and to physically prove or disprove this by not looking out there somewhere in the universe, but instead recreating a model universe right here on Earth by using tiny galaxies made out of Bose-Einstein condensates. And here, even in their own simulation, they were already able to create something resembling a dark matter halo, or basically a gravitational structure that we usually believe is responsible for holding the galaxy together. But in their simulation, they also were able to observe unusual turbulent states and unusual vortices that existed outside of this halo, all of them a result of quantum effects, assuming that this is exactly what dark matter is, should be visible somewhere out there in the universe as well. And so here, the centers of these halos seem to actually possess extremely similar properties to gigantic Bose-Einstein condensates. And the farther away from the halo you move, the more wave-like behavior and the more unusual quantum properties should be visible around various galaxies. But here, even though the core itself seems to possess Bag-like properties, outside of the core the effects become a little bit less predictable. Or I guess in simpler terms, if this is correct, the intergalactic space would potentially have a lot of unusual quantum effects that we cannot explain. And it's really these unusual vortices that seem to form as a result of the halo that would actually potentially prove this idea if we can somehow discover them in the intergalactic space. Either way though, this model actually presents the entire universe and every single galaxy in that universe as something that's more wave-like in nature, as opposed to something that's being driven entirely by gravity and particle interaction as modern cosmology presents it. And so in some sense, this is actually a pretty intriguing explanation, and an explanation that once again shows us that in some sense the universe is just a little bit stranger than we ever thought. But whether any of this is true, and whether any of this makes sense, only future studies will tell. For now, the only facts we have are that Bags are real and do possess unusual properties, and that there does seem to be some kind of an unusual effect that we refer to as dark matter. But whether these effects are connected and potentially can explain one another, or if it's completely unrelated, that's not something we can definitively answer just yet. Nevertheless, at least for now, that fuzzy, cold dark matter explanation has now officially moved up a little bit higher on the list of potential explanations for the mystery of dark matter. But if you'd like to find out about other alternative explanations, check out the previous video from just a few months ago. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, and maybe support this channel on Patreon by joining channel membership or by buying the wonderful person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.